The three quantum numbers n, m, and ml tell us about the orbitals. For example, they tell us that when n equals 3, we can have s, p, and d orbitals. And they tell us that there are 3 p orbitals and 5 d orbitals. Because of orbital shielding, orbitals with the same n value don't have the same energy. We know that the lowest energy orbital is 1s. This is followed by 2s and 2p, then 3s and 3p. But after that, we do not have 3d, we have 4s. So we need to rearrange things a bit. Now we can continue with our ordering. After 4s, we have 3d, then 4p. The fourth quantum number, the spin quantum number, tells us that each orbital can contain 2 electrons. Now our diagram of orbitals looks very familiar. It looks like a periodic table. And in fact, that is exactly how we get the shape of our periodic table. We have 4 different blocks in the periodic table called the S, P, D, and F blocks. The names of these blocks tells us which orbitals are partly filled. So let's have a look at an element from the S block, say sodium. Sodium has 11 electrons, so its electron configuration is 1s2, 2s2, 2p6, 3s1. The partially filled orbital is the 3s orbital, and that's why sodium belongs in the S block. Now we can have a look at an element from the P block, carbon. Carbon has 6 electrons. Its electronic configuration is 1s2, 2s2, 2p2. Its partially filled orbital is the 2p orbital, and that's why carbon is in the P block. Another important distinction between elements in the periodic table is between metals and non-metals. In general, elements in the S, D, and F blocks are metals. Elements in the P block are primarily non-metals, but there is also a zone of elements with intermediate properties called semimetals or metalloids. We're going to look at properties of different elements across the periodic table. First, we'll start with the S block. Elements in the S block are called alkali and alkaline earth metals. Metals in the S block tend to be very reactive and readily form cations. Because they are so reactive, they almost always exist in ionic form rather than as elements. These elements are amongst the most abundant elements in the body and in seawater. Alkaline earth metals have a number of common uses. Potassium salts such as potash are used in fertilizers. Elemental magnesium is used in electronic devices. And calcium salts are important in making bones and teeth strong. Now onto the D block, which are called the transition metals. These can exist as both metals and as ions. Transition metal cations can form both simple salts with anions and more complex structures. Transition metals can often adopt more than one oxidation state. For example, copper exists as both copper 1 and copper 2, meaning it has lost 1 electron or 2 electrons. The salts of transition metals are often very colourful, and this is important in their uses. Transition metals have a number of different uses. Elemental transition metals have very good conductivity and malleability, so they are used in electric wiring, such as this copper wire. One particular iron complex called Prussian blue has a very vivid blue colour, so it is used as a pigment in paintings. In nature, transition metals are responsible for the colour of gems. For example, the red colour of ruby comes from traces of chromium. It's important to remember that the F block fits in the periodic table between the S block and the D block. It's just generally shown below the rest of the table, so it fits better onto a page. The F block elements are called rare earth metals. The first row are called the lanthanoids, although you might also hear them called lanthanides, and the second row are called the actinoids or actinides. The rare earth metals are silver or grey metals with high electrical conductivity. Metals in each row have very similar properties, so they are very hard to separate from one another. They almost always form the 3+ cation. Common uses of actinoids are based on their radioactivity. They are used in nuclear power plants and in radiation treatment for cancer. Lanthanoids are commonly used for their light-emitting properties. Each lanthanoid gives out light of a specific colour. So they're used in lasers and as the phosphors in TV and computer screens. The P block is the most diverse of all of the blocks of the periodic table, so we're going to look at different sections in turn. Some of the P block are metals, sometimes called the post-transition metals. In general, they have similar properties to transition metals, but they're softer and have a lower melting point. They're primarily used in metallic form or as alloys. For example, aluminium alloys are used in aerospace construction, and tin is used in alloys as solder, making use of its low melting point. The exact designation of which elements are metalloids is debatable, but they do lie between the metals and the non-metals in the P block. The metalloids, or semi-metals, have properties between those of metals and non-metals. For example, they tend to be metallic in appearance, but they are brittle. They have poor structural properties, so they're most commonly used as alloys or as compounds. For example, silicon-germanium alloys are used in integrated circuits. Metalloids tend to be toxic, but this toxicity can be used to selectively kill bacteria or cancer cells over healthy cells. Compounds of arsenic and antimony, for example, are important in medicine. The non-metals in the P block have very diverse behaviour and properties. For example, they can exist as either solids, liquids, or gases, and they can form both ionic and covalent compounds. Nitrogen, oxygen, fluorine, and chlorine exist as diatomic gases, N2, O2, F2, and Cl2. Non-metals have a very wide range of uses. For example, carbon can exist as diamond or as graphite, and these two have very different applications. Most of the salts in the ocean have chloride as their anion. Finally, we come to the very last column of the periodic table, the noble gases. All these elements have completely filled valence orbitals. For example, neon has an electron configuration of 1s2, 2s2, 2p6. These elements exist as monatomic gases, and they're typically very unreactive because they have no need to gain or lose or to share electrons. Because the noble gases have very low boiling points, they're commonly used as cryogenic refrigerants. In 1937, helium replaced hydrogen as a lifting gas for blimps, as it is not explosive, and it is now used to make balloons buoyant.